Okay, let's do the lecture number 17. That's a continuation of the electrochem. The stuff that I didn't talk about, but I think you probably have seen this definition of the galvanic set and the electronic set. Just read it. I think you already know these type of things. From Genchem 2, I think. Okay. Then, let's consider the following reactions, which is these things right here. As you can see that you can actually separate these reactions into the two half reactions. One is this guy right here, the production of the peroxide, and then the other one is NADH conversion of the NAD plus. And you can combine this one and that one, add it up, you get that one right here. And this one right here, the oxygen start out with oxidation number of 0, but oxygen inside of the peroxide is -1, right? So that's reduced, so it's a reduction, right? And then for this one right here, NADH, the 0 charge becoming the +1, so it's oxidation half reactions for here. Okay, so these two separate reactions is actually happening in one of these beakers and one of the beakers here. Maybe oxidation reaction is happening here, reduction is happening here, and then you can actually take the voltage difference between these things, and then you can actually get the potential difference out of these things. That's an experiment that you may actually do in the quantitative chemical analysis, that is. And how do I actually write this equation into the I think it's called the standard form or something. I could be wrong, so go ahead and Google that. But it's this double line right here means it's just separate beakers, more or less. And then you write everything that's on one side with the physical boundaries that's denoted by this line, one single vertical line here. So solid, and then everything else is in the water, and everything is in the water on this side, and then gas and solid. And all of these guys belong to, all of those guys, yeah, can I just, yeah, let me just try to use markers here, that's better. All of these guys is for that one, that's oxidations. Oxidations should be written on the left hand side, reduction should be written on the right hand side. Okay. So this equation right here pretty much explains everything. The overall reaction is this guy right here. Alright. So in the previous lecture, we did actually talk about the non-expansion work by actually bringing the charge from the one place to the other, right? That was given by this formula right here. Now that if you actually think about the being electrons, you being the electrons, then your potential changes, right? So you can actually convert this equation in terms of the electrons. So the non-expansion work at the constant temperature and pressure, the delta G, is equal to this, but that's also equal to the negative V Fe cell. So this is in terms of the electrons point of view. So this is the number of electrons, and then this is the voltage that you measured, and F being the Faraday's constant. And you have negative signs here just because how we actually define the voltages, but the voltage Should I actually talk about it here? Yeah. Delta G being negative, being spontaneous, right? Then, because of this negative, if the voltage is positive, that reaction is actually spontaneous. The overall reaction is spontaneous. Oh, actually, I had it right here, but that's okay. So the delta G of reaction is minus nu Fe cell, right? So let's just say that you have measured 1 volt. Just change this font to be 28 or maybe 24. Okay, so you have measured 1 volt in a setup shown in a previous slide, right? And then you know that reaction had just transferring the electron just by 1 of them, right? Is that 1 or 2? It's actually 2 here. So let me just fix that one. That one is actually 2. Then what is the delta G here? So 2 goes in here, 9648 is 96480 is goes in here, and then voltage is 1, right? So you just multiply everything, then you get the joule. The unit conversion, the voltage times the coulomb is going to give you joule. So if you put 1 here and then put this number there, and that's going to give you joule per mole, which is exactly what you want here. And I don't trust this number just because that I missed this one, but I could be correct just because that I may actually put the 2 in there. So go ahead and calculate by yourself. Alright, so one other equations that actually comes out of this one, the delta G of reaction is equal to negative nu Fe cell, right? So we're going to use that one. But also that we know that the delta G of reaction is given by this formula too, right? So substitute these things right here into here, and then divide everything by the nu F, or the negative nu F, then you get these things right here. The E cell. The E cell is equal to E cell standard minus RT over nu F of the log Q. The E cell standard is actually defined as this way, so that it's going to look clean on this one. That's called the Nernst equations. And that one right there is somewhat useful because we are setting up the condition that's in a standard, right? It's remember, it's a 1 mole room temperature, and then the standard pressure, I think, standard STP, I think. Then you can actually tabulate those voltage values. And if you have the gigantic table of these values right here, then you can actually calculate the E cell by just looking at this table. So that's pretty much how you actually use this table right here. And just in case that you don't know how to use this one, I just gonna make sure that I have electrons that shows up on the left hand side, and then once you actually seen this one, that depends on the table that you're looking at, right? But this table actually has electrons showing up on the left hand side. Then what you're gonna do is that your hand is gonna move like this. I don't know how the camera is actually looking at it, but it's your hand should look like top left, top right, goes down, bottom right, bottom left. And each time that you touch the place, you have reactant, product, okay? So for this particular reaction right here, right, I have this kappa, that's my reactant. It's reactant, product, and then reactant product. Think. reactant product. So this reaction right here is a Cu2 plus zinc solid becoming some Cu solid plus zinc 2 plus, and my hand movement goes like this, right, in a clockwise motions. If your hand moves in a clockwise motions, then this reaction right here is actually spontaneous. That's what it means. And if your hand moves like counterclockwise, it's not spontaneous. Right, the other things I want to actually talk about is the E cell. What happens if the battery dies? Then there is no more reactions, right? No more transfer of the electrons. For that particular case, zero, right? The delta G of reaction is zero. That means that you cannot make these guys go to zero, so this one has to be zero, right? So the E cell is equal to zero, then E cell naught is equal to RT mu F log of Q. So the Q is going to end up in the particular concentration, so that it's going to cancel out this E cell naught. That's how you actually kill the batteries. If you wait long enough, then the reactant become product in sufficient concentration, so that it will actually become this ultimate Q that makes the ultimate Q, by the way, it's called K, right? The equilibrium constant. So yeah, that's how you make the battery die. The other things that I want to actually talk about is that sometimes the pH affect the E cell pretty big amount. So for conversion of humaric acid into the succinic acid, the half reaction is given like this. Then if you write the nasty equations, you get this one, right? But H plus, that's pH dependent, right? So you calculate the H concentration and then give it, plug this into here. Then you can actually get either the concentration at the when the battery is dead, or you can do all kinds of stuff. By the way, you notice that there is not 2 here, right? Can you tell why that I'm missing 2? Maybe the answer is somewhere here. Just a 2 square log goes in front, and then 2 and 2 cancel, right? So it was supposed to be like this, but 2 and 2 cancel. That's what it was. Alright. The last thing is that I wasn't actually ready to talk about these things in the previous glycolysis part. We actually had this reaction going from here to here, right? And that reaction was actually the reduction of the NAD plus to the NADH, right? And this reaction right here, if this is reduction, this has to be the oxidation, right? And this is how it is. This is what it is. So if you actually have the delta G of the entire process, did I actually find that one? I might have actually, yeah. Actually not. I'm sorry, I couldn't actually find the value for this one right here. But let's just say that if I found something, right, then I can probably use this delta G, and then I can get all kinds of interesting values from each half of these reactions using the nasty equations and such. Alright, the last equations that actually mentioned is these things right here. The overall reactions, and then you wanna combine these half reactions to make this one, right? For this particular case, the E cell is given, that the delta G of the reaction is also given. Then if you know one of these, then you can pretty much get another values. So I think that's probably all I wanted to tell you for the electrochem.